One nice thing about installing EMAN2 is the binary distributions, which exist for Windows, Mac, and Linux, include its own copy of Python, except on the Mac where it uses the system Python because it's so standard. Includes IPython, includes PyQt4, includes PyOpenGL, Matplotlib, and NumPy, and a bunch of other C dependencies. So the Python that you get when you install the EMAN2 binary already has all of that stuff that's kind of a pain to install on your own included in the binaries. Now, this is sort of an overview of the package. I'm not going to talk about how to do cryo-EM reconstructions today or something like that. This is still a programming class, so we're going to focus mostly on the programming side of things. But still, it's good to understand the architecture of the package. So at the base, there's a C++ library which does all of the high-performance image processing tasks. Then on top of that sits the Python core, which gives you access to those C++ routines. Then all of the command line programs are written using the Python library. And then there are high-level programs which make use of the command line programs. And then at the top level, there are graphical programs, which again are written in Python using the Qt library and make use of the Python core routines as well. So today we're mostly going to be talking about making use of this sort of Python core. I'll mention a couple of command line programs. So the package supports a fairly wide range of file formats. Most of these formats that are listed in the top here are structural biology related formats. MRC is also a CCP4 format, which is used in X-ray crystallography. Magic, Spider, PIF, ICOS, those are all sort of cryo-EM specific formats. Mirror is a general purpose 3D, 2D visualization package, commercial package, which is fairly expensive, but you can exchange data with it fairly seamlessly. Explore is a X-ray crystallography software package. We support those formats. Then down here you'll see the generic formats, TIFF, PNG. There's JPEG support, but that's write-only support. That's just for making images for PowerPoint presentations or something. As I mentioned before, JPEG, due to its lossy compression, is not suitable for quantitative image processing. So there's no support for reading from JPEG images. Honestly, if you're going to import data into the software from some other task, I would suggest TIFF is probably the most appropriate format to use. You can also read raw binary data in various ways, of course. All right, so there are a number of useful graphical user interface programs that come with the package. You'll notice they all have a .py extension at the end since they're all actually Python scripts. There are really only two of them that I'm going to show you today because they're useful if you're in the context of trying to write programs. All right. If you run e2display.py by itself, it will open up a little file browsing dialog. And it's very much like a standard system file browsing dialog, except the columns that it shows you are a little bit different. It'll show you the dimensions of the images, including three-dimensional images. So this file, for example, is a 200 cubed volume data set. It'll tell you the size, and it'll tell you the number of images in the file. So if it's an image stack, so you can see here, for example, this is an image stack, which has 154 images in it, and the dimensions of the images are 168 by 168. So this gives you a useful way of sort of browsing a directory that has images in it. When I select a particular image, you'll notice it provides a number of buttons at the bottom of the screen, which allow you to do various tasks. These are largely visualization tasks that you'll see at the bottom. So we can pick an image. So this is just a regular single two-dimensional image. You can see we only have a couple of buttons here. Let's say show 2D, and we'll see what this image is. So it's just an image of Perth, a section of an image of Perth. So it's a 1K by 1K section of that image. Now you'll notice it's black and white. So this is the one thing which makes EMAN2 not suitable for certain programming tasks because it only supports grayscale images. The images are floating point images, however. So every pixel in the image internally in EMAN2 will be a 32-bit floating point number. Okay, but no color. If you want to do, if you have multi-channel images or something like that, so if you're doing fluorescence and you have several different fluorophores that you're recording or something like that, you'll need to load them as separate images, not just treat them as one color image. So if you read TIFF images in or something like that, it'll turn it into a black and white image if it wasn't already. All of the graphical tools in the package respond to a middle click by opening up a control panel. And the control panel gives you access to a variety of different capabilities. You can use the scroll button scroll wheel, to zoom in and out of the image, of course. So we get a histogram. We get a variety of controls for doing things like interactively inverting the image. For those of you who know what Fourier Transforms are, we'll let you perform an interactive Fourier transform of the image and look at the results. This is very useful in a lot of general scientific image processing tasks. And then it'll give you controls for things like brightness, contrast, that sort of thing. If you need to make measurements in the image, we can go up here to the Measurement tab, and then we can drag lines in the image, and in the control panel, sorry, the display is kind of small here, so covering up what we're doing. So when I measure lines in the image, it will tell me how long they are and what the coordinates are and that sort of thing. Let's see, magnification, minimum, maximum, brightness, contrast. You can adjust things as brightness and contrast or as a minimum and maximum value. That allows you to also measure values of pixels in the image. There's a little basic drawing tool if you need to modify the image in some way. You can draw solid colors in the image and change its contents. And then you'll notice there's a Python tab here, which actually gives you a single line sort of interactive Python prompt where you can access attributes inside the images. Let's close that. So that was a single image. Now let's look at, say, an image stack. So you see when I select an image stack, now I have two options. I have show 2D and I have show stack. If I say show stack, it will give me a tiled display of all of the images in that file. And again, there's a control panel, but the control panel is a little different in this case. It'll have the same sort of brightness contrast controls down here, but it'll also allow us to annotate the images. If you can see in the corner there, there's a little number, and the number is the number of the image within the file. But if I want to look at something like the standard deviation of the values of the individual images or something like that, they're all 1 in this case because the images have been normalized, but I can see those values. Let's see if there's anything else in here that's used. I don't know. I don't know if these images have any parameters. So these are all of the parameters that are available, the metadata available for each of the images in this file, and we can annotate the display with those. Yeah, all right, we'll skip that. Now, if you've got two stacks which have been related in some fashion, for example, by a filtering process, I can switch from one stack to the other sort of interactively, and that'll allow me to see the change that the filter caused in the images. Now you can see that these values are different. These are the standard deviations of these images. So you can see these images have been filtered, and these are the raw versions of the images. So that's show stack. I can also open a stack in the regular 2D view, and if I do that, I still have my line there because it's the same viewer as before. You'll see that it says 1 out of 254, and I can use the arrow keys now to sort of scroll through the images in the stack very quickly. Okay. Now let's say we have a 3-dimensional data set. So this is 192 cubed volumetric data. Now I get a few more options. Now I have a show 3D button, and I have a chimera button. So I can start with the show 2D. So if I show a 3-dimensional volume using the 2D display, what it'll do is show me a slice. And I can scroll up and down through the slices in the image. And I have the same control panel I had before. Let me auto-contrast that. So what we're looking at here is a slice through the middle of a ribosome molecule. Assembly, I should say, not molecule. And the same thing, if we say show stack, we can see all of the slices through the stack. If I say show 3D, then I get a three-dimensional visualization widget, which will show me the data in isosurface form. And now if I bring up the control panel for that, you'll see that this actually has a wide range of different capabilities for 3D data display. What we get by default here is an isosurface. That's sort of like a contour plot at a single contour level of the volumetric data. So I can rotate things around. Let's see. I can also add slices through the data. So now you can see there's a 3D slice in that orientation. Let's add another slice. Okay, so now I've got slices through the data. If I turn off the isosurface, now you can sort of see those slices interacting and how there are slices through the volumetric data, and we can move them around. Oops, grabbed the wrong one. So we can move the position of the slice through the data and that sort of thing. Spin it around. So the 3D display widget has a wide range of different capabilities. It also allows you to add annotation objects. So for example, let's say we want a line pointing at something in the image. We can add an arrow, and we can move it around and have it point at something if we want. Let's see if it'll let me. Yeah, so I can rotate it around, change the arrowheads, whatever. Anyway, so that's the 3D display widget. Now I'm showing you these various widgets in this way because all of these widgets become available to you from Python once you've got data loaded into the interface. Sorry, into Python. Okay, let's see. Chimera I won't show you. That's actually a general purpose molecular visualization package, and it just allows you to launch it easily and copy your data into it. I don't think I have an example here. It actually can do the plots of two-dimensional and three-dimensional text files as well. So the last thing I think I want to show you here, well, hang on, I'll get back to that a little bit later. Let's go back to this. All right. Now, one of the keys to the way EMAN2 is assembled is it has these sets of modular classes internally. So for various types of operations that you might want to perform with these images, it has categories of routines. So for general purpose image processing, it has processors, which do things like apply filters, masks, thresholding operations, mathematical operations, that sort of thing. The number you see over here is the number of different algorithms in that category there are. So there are 175 different image processing routines that you can apply to your image data. Some work on 2D, some work on 3D, some work on both. It just sort of varies. We'll go back and look at that a little bit more later. But then there are aligners, which will take two images in 2D or 3D and bring them into registration with each other. Projectors, which are used to take 3D volumetric data and make two-dimensional projections of the data in particular orientations. Reconstructors, which do the opposite. If you have a set of projections, it'll do a 3D reconstruction. And that's the task that's used in both cryo-EM and X-ray crystallography to get a three-dimensional volume in real space out of Fourier space data that you've collected. Or in cryo-EM, we take images of individual molecules floating around in random orientations. And we take those images, we determine the orientations, and then we use a reconstructor to put them together into 3D. Comparators allow you to measure the similarity of one image to another image in a particular location. Averagers do what it sounds like. They average a stack of images together. Analyzers, we may talk about briefly later, they allow you to take stacks of images and perform some sort of image analysis on them, like k-means classification or principal components analysis or something like that. And orientation generators are used to generate uniform orientations on a sphere. Won't go into that one too much. So here are some examples of the different categories of processors that exist in EMAN2. So we've got filters, masks, mathematical operations, normalization operations, thresholding, geometric transformations. So given that there are close to 200 of those, it's sometimes a little difficult to grasp what's available and figure out how you would deal with it. So let me just show you how you'd find out about them and how you'd experiment with them most easily. Now, you could, of course, experiment with them from Python, but it's actually easier to do that in a graphical method. So let's see. All right, if you want just a list of all of the available processors, there's a command called e2help.py, which will give you help about any of those modular classes that we were talking about. So if I say e2help processors, it will give me a list, and I'll scroll by pretty fast there, of all of the available processors. Now you could look through that list, or you could search through that list for a particular word that you thought might be there. Or we can use a program called filter tool. So filter tool, let me do this on, here we'll use our Perth image again as a test. So you run filter tool on a single image file. It could be 2D or 3D, your choice. And what it will do is open up a window which shows you the image itself. And it'll open another window which allows you to add processors in sequence to it. So let me start out from scratch here. I'll make a new one. Okay, so it'll start out looking like that. I'd already done something in this directory, and it remembers between sessions what you'd set up. Okay, so here's our original image. Maybe I'll set the scale. Again, you get your control panel as always. I'll set the scale to 1, so we've got 1 pixel to 1 pixel. Then I can look at categories of filters, and then once I've picked a category, I can pick a subcategory. So let's say I want to do a low-pass filter. Okay, a low-pass filter would be blurring the image. So I say filter dot, then we've got a whole bunch of filters here. So we've got filter.lowpass.autob, filter.lowpass.butterworth, Gauss, random phase, tangent, etc. So we'll do a Gaussian low-pass filter. That's equivalent to what would happen if you're using like a digital camera and you had it out of focus. Okay, there are a variety of ways I can specify these arguments. If I mouse over one of the arguments, it'll give me a little help line which tells you what each of those arguments means. An absolute cutoff will define the amount of blurring that happens in the image, basically. Where if the number is low, it blurs a lot. If the number is large, it doesn't blur very much at all. The largest value is 0.5, and the smallest value is, well, sort of effectively it's 0.5. I'll show you what it does. So you'll notice there's a little checkbox next to each of these, and there's a little checkbox up here at the top as well. If the checkbox isn't checked, then it's not using that parameter at all. And in this case, it's not using the filter at all because I haven't checked this one. When you first create the new processor object, it doesn't check the object because you might need to set some parameters first. It may be invalid when you first set it up. So I'm going to set cutoff absolute, and then I'll go ahead and check the checkbox, and you'll see the image changed immediately. Okay, you see how it's a little blurrier now? Now if I drag this out to 0.5, you can see how it gets sharper. And if I drag it all the way over here, you can see it gets really, really blurry. Right? If I want to specify an exact value, I can type in the text box as well. And if the slider doesn't actually go to the full range that I want it to go to, I'll show you that in a second, actually. All right, so I've got my my Gaussian blur here. So we'll blur my image out. Now let's say I want to apply a mask. So I can hit the little plus button here, and that'll add another processing object. Now I will say, let's see, mask dot sharp. So there's a variety of types of mask. This is just a sharp circular mask. And the sharp circular mask has inner and outer radius. So it'll actually allow you to make a ring, not just a circle. And then it'll have a shift from the center location. Let's go ahead and turn that on and we'll see. Image became black. That's because my outer radius was set to 0. So let's drag that out. Oh, now we can see something appearing in the middle, but you can see the maximum range of this slider is only 5. Okay? I could type a larger value in, or I can adjust the range of the slider by typing less than or greater than a value. So in this case, the image is 1K by 1K, so I would want a radius of at least, say, 500, at least the capability. Okay, so as I'm doing this, it's interactively performing both filters in the sequence. So every time I change any of the parameters, it recomputes the entire chain. There's only 2 in the chain right now. Now you'll see that we've done a Gaussian blur on the image, but the edge is sharp because that's the order the filters have been applied in. Right? So first I'm filtering the raw image, and then I'm applying a mask to the image. If I use these arrows, I can adjust the order of the operations. So if I shift this up here, okay, now if you look, now you'll see the mask is also getting blurred because now it's masking first and then it's filtering. Okay, so I'm not going to take you through all 176 or something like that operations, but I'll just show you that, showing you that this tool exists, and this is a very good way of sort of preparing for writing your program in Python. So you can look at this and you can decide which sequence of filters you might want to use, and then you can write a program to actually implement them. As I mentioned, you could use this program on 3-dimensional data as well. I'll just do that really quickly. We'll open up our ribosome again. Oops, and like usual on the Mac, we have to click on the window to get it open. Oh, and of course, it's using the same filters that I'd set up before, so let me get rid of those. All right, let me just start this again, just to get the defaults right. Huh. Oh, I see what's going on. I just don't have a good isosurface set. There it is. The isosurface threshold I was using was just too high. Okay, so you can see this looks kind of noisy. And in fact, if I lower the threshold even more, we'll see there's actually a lot of high frequency noise present in that reconstruction. So let's say I want to do a low-pass filter on that data to get rid of some of that noise. So we go back here, and we can say filter. And again, I'll just use the low-pass Gauss filter, and we'll turn it on. Now you'll notice this is going to be a lot slower because it's doing 3D image processing. Every time I grab this slider and move it, it's performing a 3-dimensional filter on a 192 cubed volume of data. So it's not going to happen as fast. And that's one of the reasons. Although I'll point out that you can see the slider is actually fairly responsive. It's just that the updates on the screen aren't as fast. So it actually does let you drag the slider faster than it can do the computations. Anyway, so that lets you play with interactive filtering of your data. All right. All right, so categories of processors. So let's actually get into using EMAN2 from Python directly now. So EMAN2 comes with a handy script called E2.Py, which basically runs IPython in a mode where a lot of the EMAN2 stuff has already been imported for you. So if you remember when we were using SciPy, there was an option you could say IPython-Pylab, and it would import all of the Pylab stuff for you. E2.Py is something similar. Technically, I could also say IPython and then from EMAN2 import star, and I would have more or less the same effect, but not exactly. And I'll show you what I mean. Okay, so yeah, it's fine. We can just go through some of this. All right, so let's make a test image. So there's a function called test image, which just makes sort of a general purpose two-dimensional test image. So there's a nice function called display, which is good for interactive use, which will take pretty much any object that it's capable of dealing with and open up a window to display it. If you pass it a stack of images, it'll open up a stack display. If you pass in a single 2D image, it'll open up the 2D image display. If you pass in a volume, it'll open up a volume, etc. So in this case, we've got a 2D test image. We say display A, and you'll see that we got this error message down here where it says invalid frame buffer operation. This is a Mac. This isn't an actual error. This is actually just a warning message on the Mac. The current version of Mac OS has a bug in the OpenGL implementation, and it spews out these warning messages all the time. But it was actually harmless. If we look over here, we should have a little rocket ship still. Oops. Come on, wake up. There we go. So we actually got our window. So here's our test image. And just like what we saw in the other program, we get all of the capabilities with the control panel on our test image. And we get our Python prompt back. So we can actually modify the test image in place. Make this window a little smaller here. So let's see. Let's access a pixel in the image. So my image is called A, and that's a libpy emdata2 emdata object. So emdata is the image class in EMAN2. It represents 1D, 2D, or 3D image data. If you want to access pixels in the image, you can just say A with square brackets of, say, 2020. And it'll tell me the value of that pixel, which is exactly 0 in this image. So let's modify the value of that pixel. Say A of 2020 equals 25. And you can see the pixel value appeared interactively there. So as we're modifying the image, we can see it changing interactively. We can do some simple math. We could say a.mult -1, and we can invert the image data. Now we might want to adjust the display threshold once we've done that, but anyway. Okay, so that's sort of the basic, most straightforward stuff. Oh yeah, I was going to show a couple of display examples. I can make a three-dimensional test image. I can say test image 3D. Oops. All right, I don't want to do A because then I'll lose access to my current image object. I'll call it B. And you can see again, B is an emdata object. If I say display B, we'll get a 3D display up. And that test object is basically just a set of X, Y, Z axes. Again, I can open a control panel and do all the stuff I could normally do with that widget. Then we can do the last one. Let's do this. If I say display on a list of numbers, it will plot it in 2D for me. And I can give it X, Y data pairs as well. This plotting is done making use of matplotlib, but it has its own control panel. So if I middle click on it, I'll get up a nice control panel where I can adjust some of the properties of that plot interactively. It also allows you to zoom using the right mouse button, and the left mouse button will give you crosshairs and tell you what's in the image and that sort of thing. Okay. Now, display is very useful for interactive use. We'll get to this a little bit later. If you're writing your own program using the EMAN2 library, though, you don't want to just use display because you won't know what kind of object you're getting back. You can actually create instances of individual widgets of specific types. yourself, and we'll get to that a little bit later on. All right, so how do we create an image? The only images that we've created so far have been these test images. So the EM data object, as I said, is the, sort of the image object in EMAN2. So you can just say EM data, and that'll make an empty EM data object with default size. But normally you'd want to say how big the image is. So you say EM data and give it the size in X, size in Y, and size in Z. If you want to have a 2D image, you set NZ is equal to 1. If you want a one-dimensional image, then you set Y and Z equal to 1. You can also initialize it from a file, and we'll look at that on the next page. And once you've set up the image, it's good to have these 2, 0, and 2, 1 functions available, which will set all the pixels to 0 or all the pixels to 1 in the image. Okay. Reading images from file, very straightforward. I can take an existing EM data object, and then I can use the read image method on it, or I can create an EM data object and also pass it file name and an image number. So here are the various options available. You give it a file name. Image number is for stack files. So if you have a single file that has 1,000 images in it, that'll allow you to pick one of the images for reading in. The square brackets options here are optional. In other words, you have basically, actually technically image number is optional too. So you have to give it a file name. You can give it an image number. If you don't give it an image number, it'll take the first image from the file. Header tells it not to read the image data itself, but just to read the header data for the image. So it'll tell you how big the image is and all of the other metadata about the image. This allows you to read a region. So say you have a 4K by 4K by 1,000 volume data set, which is I don't know, what would that be, like 60 gigabytes on your hard drive. So you have a single image file, which is 60 gigabytes. You probably don't want to read the whole file into memory at once. Region allows you to read just a section of that off the disk into memory. So it'll allow you to read a subregion. And 3D isn't something you normally have to specify. That'll give it a hint. There are certain file formats where they store 3D volumes and stacks of 2D images in the same way. And this allows you to tell it that it's a 3D volume, not a stack of 2D images. We're going to skip this stuff down here. It doesn't really apply today. So let's give that a try. So if we look in our directory, we have this, here's that image of Perth that we had. Let's go ahead and give that a try. So I've got my image A, which is displayed here. So A is already an EM data object. So I should be able to say a.read image like that. And ta-da, it overwrote my image with this new image. Now, of course, the contrast isn't set right. I'll have to auto-contrast it again, but there it is. So there's the image we've just read from disk. All the file formats supported by the package are handled transparently. So if it's a supported file format, you just say read image and it'll recognize what file format it is. If it's a file format it doesn't recognize or can't read for some reason, it'll complain. I suppose we could try volume data too, but that's basically the same way, done the same way. Make this a little bit bigger so I don't have to keep switching back and forth between presentation mode. All right. Writing images is similarly straightforward and has a very similar interface. Instead of read image, you say write image, give it a file name, optionally an image number if you're creating an image stack. So it will normally look at the file name you specify, and that'll be how it decides what file format to use. If you want to use a funny extension for your file, which it won't recognize, you can use the funny extension, and then you can specify in the type section what file format to use when it's writing the image. Again, you can tell it to write just the header, not the actual image data, and you can tell it to write to a region of the image. So this region reading and writing is very convenient if you, as I say, you have one of these large files. So there's a field called cellular tomography, which involves doing three-dimensional reconstructions of cells or sections of cells. And this is done both by cryo-EM. It's also done by X-ray tomography. So there are a number of sites around the world now which have X-ray tomography capabilities. You can look at whole live cells at resolutions approaching 100 nanometers or something like that, or 50 nanometers. Anyway, if you've got one of these very large volume files, it's very convenient to be able to read out a chunk of it, process it in some way, and then put the chunk back in the image again without having to read the whole thing into memory. All right, pixel data, yeah, we already mentioned that. You can just access pixel values as XY or XYZ coordinates. So A of 50, 50 will give me the pixel value there, and I can modify the value just by saying A of 50, 50 equals. I mentioned Fourier Transforms before. This isn't a math class, and teaching Fourier Transforms takes a couple of lectures. If you know what a Fourier Transform is, they're very straightforward to do. You say D equals do FFT, A dot do FFT. It's a method on the EM data object. And now D is a new EM data object, which is the Fourier transform of A. I can say display D. And there's my Fourier transform image. And if I access pixels in D, instead of getting real numbers out, I get complex numbers out. So this is 780 million? No, sorry, 78 million. And then it's got a J over here, which is the complex square root of -1. So I can set and get complex values if the images are in Fourier space. Okay, image attributes. So each image that you read in has a wide range of different standard attributes. For example, if I look at, I've got A, I can find out the mean value in the image like this. So the square brackets serve two purposes in this case. It can act sort of like a array of arrays. It can act like sort of a matrix if I pass in tuples of numbers, or if I give it a string, it can act sort of like a dictionary, and it will return values associated with things. Some of these attributes, like the mean or the standard deviation, are automatically calculated for the image. Other values are stored in the file on disk and read with the file when you read the file in. Now, if I want to get a list of all the attributes associated with the image, I can say get, so there's I can say get attribute instead of using that square brackets notation and give it a name like mean. Oops. Or I can say get attribute dict. And that will show me all of the attributes associated with the image. Okay, so you can see I read this image from a TIFF file, so there are a few header values associated with that TIFF file. Each of the supported file formats will have different metadata associated with them. Then there are sort of some standard values here. This is angstroms per pixel. It's mostly useful for structural biology. If you're not doing structural biology, then you can probably ignore those. We have things like is complex. That's if you're taking Fourier transforms, then the image becomes complex. Maximum, mean, minimum. This is an interesting one. This gives you the mean value of the image, but it ignores any values that are exactly 0. In this case, the two values are almost exactly the same. Not quite, because I guess there must be a few zero pixels in there. But NX, NY, and NZ, these are good. These will tell you the dimensions of the image. Yeah, and then this is also useful. It'll tell you the file name that the image was read from and the image number within that file. So when you read an image in, you can tell what its dimensions are immediately just by saying A of NX, for example. If you want the full list of sort of standard supported attributes, it's on one of the pages in the wiki. This is a lot of the list. So these are values that are sort of automatically computed for you. These are values that are just stored in the header, which are sort of standard across the package in multiple cryo-EM imaging packages. And then these are some format-specific ones. It's only showing the first few. These are the ones for the MRC file format. But as I say, each of the file formats that are supported has its own set. If you go into the wiki, you can see all of the different attributes and what their names are. Here, let's go to So here's the introduction to programming page. If you go up to the top here, you can see we're actually in sort of in the EMAN2 wiki. If we click here, we can get to the EMAN2 page. There's a download link. And if we go into the documentation under file formats, image processing functions, mathematical conventions, this is the page that stores all of the attributes that you can get for images, and there's a lot of them. It goes on for a while. Oops, wrong way. Okay. If you're working in a different discipline and you're interested in doing some of the scientific image processing, you say, oh, hey, I've got this file format, but EMAN2 can't read it. How would I deal with that? If you just ask for it, generally we'll implement new file formats on the fly. So just put a message in the Google group or email me or come and talk to me or something, and we can usually add new file formats. Right, so I did a little bit of math with images, but I didn't sort of show you the full capabilities. So say I've got, let's see, I showed you that, so I've got my image A. Let me get rid of this, don't need that anymore. All right, so I've got my image here. Let me see, do I have another? All right, here, let's do this. All right, I think this image is the same size as the first image. This isn't going to be very useful, but it's we'll see how it looks. All right, so this is an image of the Orion Nebula. You can see it's kind of noisy, so we can scale it up and down. All right, so let's take, so make sure the dimensions are the same first. Okay, so same dimensions. So let's take A and multiply it by B. Okay, so now you can sort of see the one image overlaid on the other image because it was after it was multiplied. Could have added A to B as well. Now I did it this way. When I said A.mult B, I was doing that in place. So it was modifying A by multiplying it by B. Oops. Let's go ahead and read back the original image there. Okay, need auto contrast again. Okay, back to original image. So you can do general sorts of math operations on your images. I can say A equals B times 2 plus A, or something like that. And that will replace A with a new image, which is B times 2 plus A. Now you'll notice this didn't change. That's because this is showing me the original A, and I just lost my access to that original A when I overwrote A with this new image. If I want to get that new one, I'll have to say display A. And there we go. Now you can see this was added this time instead of multiplying. But you can sort of see the Orion in the background there. So we can do sort of general purpose math. Let's see, what's next? Oh, interesting. I have 2 pages with create image, I guess. All right, fine. Okay, filter tool we've already talked about. Once you've figured out what the parameters are and you want to actually do some of the image processing operations, there's 2 methods that you'd call, process or process in place. So let's say I want to take this image I've got right here and I want to apply a low-pass filter to it. I would say a.process in place. In place will modify the image. If I say process without the in place, it'll return a new image which has been processed in the requested way. And I give it the name of my processor, which would be filter.lowpass.gauss. Oops. Hit the wrong button. And then I give it a dictionary with parameters. And those parameters were the parameters that I was adjusting with the sliders. So in this case, I want cutoff ABS, and we'll set it to something like 0.05. So that's going to be a fairly strong blurring filter. And there you can see it became blurry. So any of the processors that I want to apply basically get applied in the same fashion. And as I mentioned before, I'll go ahead and exit here. I can say E2 help.py processors. I can get the list of the processors, and then next to the list of processors, it'll have the parameters for each one and what type of parameters, whether it's floating point or integer or string or something like that. And if I want more details, I can add a -v2 that's verbose equals 2, or I could say --verbose equals 2. And it will give me sort of the full documentation. Sorry, the window is kind of small, so it all wrapped around in a strange way. But for example, here is the name of a processor, here is what the processor does, and here are the parameters with the documentation for each parameter. Let's see. Next. Yeah, I've already talked about filters a little bit. Some of the processors have multiple ways of specifying the same information. So for example, when I'm doing these filters, I can specify cutoff ABS, cutoff frequency, or cutoff pixels. And those are 3 different ways of specifying how much filtration to apply. Usually in the documentation, it will give you some indication of when the parameters are actually the same thing. Comparators give you a mechanism for comparing the similarity of 2 images in different ways. There are a wide variety of comparators. List a couple here. We've got dot, Fourier ring correlation, phase residual, square Euclidean distance. So there are actually a lot of different mechanisms that people who do serious image processing will use to see whether image A is similar to image B. And these metrics can be used when you're aligning 2 images to each other. So if you have 2 images, say they're noisy, and you're trying to bring them into register with one another, what you sort of effectively can do is you can take image A and keep it fixed, and take image B and shift it, say, 1 pixel at a time to all possible different locations, and then use one of these comparators to measure how similar the images are to each other in some way. All of the modular functions work in pretty much the same way. If I say e2 help.py cmps, I can see all of the available comparators. The simplest one is CCC, which stands for cross correlation coefficient. It's just a dot product between the images. Dot actually does basically the same thing. Let's try this. Actually, so I'll read my Orion image in, and then we'll read the Perth image in. And then we can do something like this. A.cmp ccc b, and then I can pass it options if I want, but we'll just do it like that. So I can pass it a dictionary of options, for example, -0. I'll explain that in a second. So that tells me that the cross-correlation coefficient between those 2 images is 0.0589. The maximum value for cross-correlation coefficient is 1. The minimum value is -1. So that tells me that there's virtually no correlation between those 2 images. So if it was -1, that would mean the images anti-correlate. So if I took the image and the image multiplied by -1, and I compared those with each other, then that would give me a -1. If you get a 0, that means they're almost completely dissimilar. If I don't put that negative 0 in, though, the value I get out is actually minus 0.05. So there's a convention that's used for these image comparisons, these similarity metrics, which is the smaller the value is, the more similar the images are. So if you're taking a dot product between two images, when the dot product is 1, obviously they're the most similar. So it multiplies the values by -1 to follow the convention, so the negative values are the most similar. And the reason you have that convention is because other metrics, like, for example, if you take the difference between the images and compute the variance of the difference, the more similar the images are to each other, the smaller that value will get. So most of the metrics that you would tend to normally use they're measuring how different things are, so the smaller the differences are, the more similar the images are. So if there are any metrics that you use that would normally return a larger value, they get inverted by default, but you can turn the behavior on and off. Probably more detail than you needed. Okay, rotations. So you can do rotations in 2 dimensions, or you can do rotations in 3 dimensions. And since we deal with 3-dimensional data, we have to consider 3-dimensional rotations. Any 3-dimensional rotation can be specified in terms of 3 numbers. There are a lot of different ways of specifying the 3 numbers, but you need 3 numbers to do it. No more than 3 and no fewer than 3. It takes exactly 3 numbers to describe an arbitrary rotation in 3 dimensions. Now what we're looking at here is the z(z) prime convention for Euler angles. What that means is we rotate around the z-axis, then we rotate around the x-axis, then we rotate around the new z-axis. And that's one combination of rotations which will give you an arbitrary rotation. There are a number of other styles as well. For example, there's a spin axis notation, which is very similar to something called quaternions, where you say, I'm going to give you an axis, a direction, and I'm going to rotate by a certain amount around that axis. Now, if you think about it, that's 4 numbers, right? I have a vector, a direction for the axis, and then I have an amount of rotation. And I just told you you only needed 3 numbers. Well, what you can do is you can represent the 3rd number as the length of the vector. If you think about it, if the vector length is 0, then that means no rotation at all. And it doesn't have a direction associated with it. But if it's no rotation, then it doesn't need a direction associated with it, so it works out fine. So in other words, you specify direction, which is the axis that you're going to rotate around, and then an amount of rotation by the length of the vector. Sometimes you actually represent it as 4 values, but that 4th value is redundant. Now, it's a little hard to picture that, with this, you could say, oh, yeah, okay, I guess maybe I can see how that would let you do any arbitrary rotation. It's a little less obvious that by rotating a single time around a single axis, you can achieve any rotation. But it's true. You can prove it mathematically. So these are the different rotation conventions that are supported by the library. The thing on the left there is sort of the names of the different software packages that implemented these different conventions. And then at the bottom here we have the spin angle. This is something specific to SGI computers back when SGI computers really still existed, and then quaternions. And these actually take 4 parameters rather than 3 parameters, even though one is sort of redundant. No, I don't expect you to remember all this or anything like that. I'm just saying, at least you know it exists. If you want to do any of these rotations translation objects, there's a class called transform, which represents both 2-dimensional and 3-dimensional transforms. And you generally pass it a dictionary, and you pass the various parameters into the dictionary, which include rotational parameters and translational parameters. So the tx, ty, tz parameters are shifts in x, y, and z. And you can get the parameters out in different notations, put them in different notations. If you're just doing a 2D transformation, there's only one style, and that's alpha is the angle, and then you have an x translation, a y translation, a scale factor, a mirroring factor. Let's go ahead and give it a try really quick in 2D anyway. All right, so Let's use B. Okay, so I've got my image of Perth again. Let's say I want to rotate and translate that image a little bit. So we'll say, so we're going to create a transform object. Type will be 2D, alpha. There are default values for most of the parameters. We'll rotate it, say, 15 degrees. And translate it 50 pixels in X and minus 25 pixels in Y. Okay, so I didn't do it yet. I just made a transform object. Now I can say, was that A or B? B. B.transform X. Okay, so it's that straightforward. Let's see. I'm going to skip over the rest of this transform stuff. It's not all that useful. Now, this might be useful to some people who are really doing some serious image processing stuff, so I figured I'd cover it briefly. There's a class of routines called analyzers, which are designed to perform some sort of image analysis on a stack of images. There's something called k-means classification, which allows you to classify images based on their mutual similarity to one another. That's implemented there under with the k-means analyzer. Here, let me do the E2 help here so you can see it. So you can see there's a k-means analyzer. Then there are 3 different analyzers which basically do something called principal component analysis, and then there's something called Verimax, which is related to principal component analysis. PCA, if you've ever taken a class on ProbStat, something like that, is a statistical analysis method which was first developed by people basically accountants for the insurance industry. The idea is if you have a whole bunch of data and you don't know how the data may be correlated, it allows you to find the strongest correlations in rank order among a stack of data. So if I have, I didn't bring along a very good example for this. Let's say I have a whole bunch of photographs, and the photographs are of 3 different people. But the images are really, really noisy. It doesn't have to be noisy. It could actually be the same people, but under different lighting conditions or something like that. And I have a big stack of these images, like 100 of them. And I want to classify them, and I want to pull out, just the 3 different faces. So principal component analysis would be one mechanism which would allow you to do that operation. Now, they'd all have to be sort of scaled the same way for it to work properly and be more or less the same orientation, but it would say, it would find sort of the strongest differences among the set, and then you could use those differences to separate the data out into multiple groups. In any case, there's a principal component analysis algorithm present here, which you can use for that purpose. And it's fairly straightforward to use. You get an analyzer object, you tell it what parameters you want it to use, and then you just insert a whole bunch of images into it, call analyze, and it gives you the result out. So it's sort of a 4-step process. And again, there's no way I can make you an expert in doing any of this image processing in a 1 hour, 1.5 hour lecture. My goal here is just to sort of expose you to some of the different things which are available so you can play with them later on if you want to. I mentioned if you were writing your own programs, you didn't want to just use the display function. You should make your own widget objects. So this is just the names of the various widget objects. Let's go ahead and just give that a try. For example, we'll make a EMImage2D widget. Okay, so I need to import EMImage2D. Okay, that's what was before the dot here. So each of these widgets lives in a different module, which is similar in name to the name of the widget itself. I'll make a test image. And then I'll say W equals EMImage2D widget. And I've created my widget now, but I don't see anything on the screen. I have to actually tell the widget to show itself. Okay, now my widget is there. There's nothing in it because I haven't put any data in it yet. I can say set data A, and now my image is displayed in the widget. And now that I have access to this widget as W, I can use any of the 521 different methods available in the widget, which will allow me to programmatically change any of the settings, or do all sorts of things to the widget. Let me just see, set histogram, set other. Here, let's try set scale. Oop, it's not centered anymore, so I lost it. There it is. It just moved off to the side. When it scales, it zooms in the middle of the display. So I had it in the corner, so it sort of zoomed off the screen. Okay. So basically, this gives you a PyQt widget object, which you can control in various ways. If you want to do anything with any of these widgets, you're going to have to learn Qt programming. But if you're going to ever do any serious GUI programming, then I think that's probably a good toolkit to use in the first place. So I'm not going to teach you how to use PyQt today, but if you just think about it, very much like the other toolkit we were using, when a user clicks on the widget, it would normally produce a callback. Qt has a slightly different style of doing things. Instead of using callbacks, it uses connections between objects. You say connect this widget to this function, which means you can connect a particular function like a mouse click in one widget to multiple other functions. You don't just get one callback, you can have multiple callbacks. But regardless, aside from that subtlety, what that means is you basically create your widgets and then create connections to the functions which tell what you want to happen when the user clicks on things and that sort of thing. Okay, so I think that's pretty much all I wanted to cover in image processing.